Namaskar everybody and welcome to online classes. This is my lecture number 36. I am Dr. P.S. Kaushik, Principal at Sri Digambar Institute of Technology, Dosa. In this lecture, we will be studying about the shear stress, shear strain, modulus of rigidity, etc. And we will be solving some problems concerned. Shear stress and strain. When a body is subjected to two equal and opposite forces acting tangentially across the resisting section, as a result of which the body tends to shear off the section, then the stress induced is called shear stress. The corresponding strain is known as shear strain and it is measured by angular deformation accompanying the shear stress. The shear stress and shear strain are denoted by Greek letter tau and phi respectively. Shear stress tau is a tangential force upon resisting area. Refer to the figure below. There is a rivet. This is the rivet and holding two plates, the red plate of upper one and the lower plate. When we pull these plates like this, there will be a stress here at this here, in which the upper part will slide over the lower part as shown in the figure this. Due to this force, the upper part is sliding just that this is the area under consideration for the shear stress. Area is, if d is the diameter of the rivet, then area is pi over 4 d square. P is the force, then shear stress will be tangential area upon resisting area. This is the resisting area over here. Consider a body consisting of two plates connected by a rivet. The tangential force P tends to shear off the rivet at one cross section as shown in figure. It may be noted that when the tangential force is resisted by one cross section of the rivet, when shearing takes place at one cross section of the rivet, then this is called single shear, and in that case area is pi over 4 d square and the stress developed is P upon A, P over pi by 4 d square or 4p upon pi d square. This is the case of single shear. Next, take the case here. In this here, these are the rivets holding these two plates with the cover plate, this one and this one. When we apply a force here, the rivet will shear at two planes, here and here. So it is double shear. So effectively the cross sectional area is doubled than for single shear. Here also we will do that. So for the shear stress developed is P upon 2 area. 2A, that is one area this, other one is this. Then P upon 2 into pi over 4 d square, which comes out to 2p upon pi d square. So here stress will be less compared to just half compared to single shear. Shear modulus or modulus of rigidity. Similar to Young modulus, here tau is proportional to phi or tau equal to c phi, where c is the constant of proportionality known as shear modulus or modulus of rigidity. It is sometimes also denoted by N or G. Different authors denote it. Some here we have noted it by C, Someone will denote it by G or N. Let us work out an example. Calculate the force required to punch a circular blank of 60 mm diameter in a plate of 5 mm thick. The ultimate shear stress of the plate is 350 Newton per millimeter square. Here, consider that this is a sheet from which this much of blank is to be removed, whose thickness is T equal to 5 mm, and the diameter is 60 mm. Hence, you can consider it that it is an area whose length is pi d, and thickness is T. So, here you can say this is not tau, it is T basically. So, we know that area under shear is pi d into T. D is the diameter, T is the thickness. So pi into 60 into 5 is 942.6 millimeter square, and force required to punch a hole P is equal to A into tau ultimate, tau u means the maximum, which is given as 350 Newton per millimeter square. So it comes out to 942.6 into 350, which comes out to with 329.91 kilonewton. This much of force is required to punch a hole there. Again, one more example. A pull of 80 kilonewton is transmitted from a box X to the bar Y. A pull of 80 kilonewton is transmitted from a bar X to the bar Y. This is the bar X. This is the bar X, this is the bar Y. Through a pin, this is the pin available. As soon as if the maximum permissible tensile stress in the bar is 100 Newton per millimeter square, and the permissible shear stress in the pin is 80 Newton per millimeter square, find the diameter of the bar and the pin to sustain this load, 80 kilonewton force. So, first realize the strength of the bar in tension, that is diameter of the bar, that is if area is AB is pi over 4 dB square, this much. Then we know stress is equal to force upon area. If working stress is given there, which is tensile is 100 Newton per millimeter square. So 100 into P upon A bar. So area is now in terms of diameter. So on calculation, diameter comes out to be 32 mm. How? What you want to say? That you have to find the diameter here. This diameter we have to find that this bar can bear the tensile load of 80 kilonewton, such that the stress in the bar does not exceed 100 Newton per millimeter square. So 100 Newton per millimeter square is the limit here. We have applied here, and we have applied the simple formula. By first we found the area of the bar in terms of diameter, which was this much. When we put the value here, then diameter of bar comes out to be 32 mm. Diameter of pin, the pin is in the let dp the diameter of pin. This is the tensile load. P tends to shear off the pin at two sections, AB and CD. Therefore, the pin is in double shear. Here, when we pull this like this, the pin will get sheared from here and at this point. Those 2 points it will shear off at the same time. So it is in double shear. So its effective area is doubled. So AP is 2 into pi over 4 dP square. That is 1.571 dP square. We know the perceivable shear stress is given 80. So 80 is equal to shear force upon area of cross section. On calculation, this again comes out to be 25.2 mm. So pin diameter should be 25.2 mm, whereas the rod diameter should be 32 mm. Linear lateral strain, very important. Consider this circular section. This is a circular specimen. It is being applied with a tensile load P. When we are increasing the force on it, its length is increasing, but since the material total volume of the material is same, hence its diameter will decrease accordingly. You can visualize this by pulling your finger. You will realize when you pull your finger, its diameter decreases when its length is increasing. Similar is the case in engineering materials also. So here the linear strain is equal to change in length upon original length, where lateral strain is change in decrease in diameter upon original diameter, or decrease in cross sectional dimension upon original dimension. This is a lateral strain. So you can read it out now. Consider a circular bar of diameter D and length L subjected to a tensile force P as shown in figure. A later consideration will show that due to the tensile force, the length of the bar will increase by an amount delta L and the diameter decreases by an amount delta D as shown in the figure. Here it is shown here, diameter decreases and length increases. It is thus obvious that every direct stress is accompanied by a strain in its own direction, which is known as linear strain, and an opposite kind of strain is every direction at the right angle to it is known as lateral strain. Poisson's ratio. It has been found experimentally that when a body is stressed within elastic limit, the lateral strain bears a constant ratio with the linear strain. So, lateral strain upon linear strain is a constant, for it is a material property. It depends upon material to material. Then it is called Poisson's ratio. It is denoted by 1 by m or mu. Values of Poisson's ratio for commonly used materials is as given below. For steel 0.25 to 0.33, cast iron 0.23 to 0.27, copper 0.31 to 0.34, brass 0.32 to 0.42, aluminum 0.32 to 0.36, and so on. Concrete very less, that is 0.08 to 0.18. rubber 0.45 to 0.5 highest. Now comes the complementary shear stress, very important. Consider this rectangular section of unit thickness. Let a stress is applied here on this face. Shear stress is applied here. So there will be a stress on these two faces also. If there is no stress there, then there will be a couple and it will start rotating like this. To counter that, there will be a stress developed here on this face like this, which will be in opposite direction. To counterbalance these stresses which are complementary to these two is called complementary shear stress. Note that shear stress is denoted by half arrow. Normal stress is denoted by complete arrow. So here half arrow here and half arrow this side. Half arrow here, half arrow this side. Then a shear stress developing on the faces which are normal to this, the opposite faces they are here, which their direction will be such that they will counter the couple formed by these two stresses. So couple produced by tau is tau into BC. It is tau, it is say tau dash. Then tau into BC is the couple produced here. Couple produced by tau dash is tau dash into CD into BC. First of all, you have to convert this stress into area. We have taken we have taken the width as unit width 1. Width is taken 1 and the dimension is AB, BC, CD and DA. So area of the face BC is 1 into BC. 1 into BC is the area. If tau is the stress, then to tau ho gaya, and its arm will be that AB will be its arm to produce a couple. And to counter this couple, this tau dash here, this is tau dash, converted into a force first, tau dash into DC into 1. We have taken its thickness 1. So tau dash into DC or CD into 1 is the force and the BC is the arm. And the force into arm becomes a couple. So equate them each other. Tau into BC into AB equal to tau dash into CD into BC. Hence AB is equal to CD. So you can say tau equal to tau dash. So complementary shear stress will be equal to the linear or normal shear stress. Here is again, we have tried to calculate it like this. Thanks for watching this video lecture. The content is taken from Machine Design by Horace Kurmi and Engineering Mechanics by Dr. D.S. Kaur.